Hello, my name is Darun. I'm from UG3. So I had implemented AES Encryption and Decryption in Ping Z2 board. So the purpose of using this board is it's because easy, because it's Python compatible, and we can able to control everything with this Jupyter notebook. So it's like algorithmically easy, and we can able to implement in ease compared to other boards, and it has more capabilities. So right now I connected a Ethernet cable to the laptop, and after that a USB power to a laptop, so we can able to communicate through laptop to the ping board, and we can able to play around with it with the Vivado and Jupyter notebook to get our things done. So I'm going to show you what is the AES encryption, decryption, everything, and I have used this hardware because we can able to accelerate it, because I'll show you in a while. So AES stands for Advanced Encryption Standards. So it is widely used in secure communications between systems, so people can't able to get the things out. The main goal of the project is to design an AES hardware accelerator using high-level synthesis and integrate it into a Zinc FPGA using Vivado. So in traditional systems, encryption is done using software, which takes a lot of time to get the things done. So in this project, AES is implemented as a hardware IP, and it's because the FPGA performs encryption faster due to parallelism, and the processor sends data to hardware and gets the encrypted data output. So I will explain that Vivado flow in a while. So coming to that algorithm, so we get a plain text, and it will go around like a certain mathematical rounds like SubBytes, ShiftRows, MixColumns, and it will finally going with XOR gate and combining with the round key to get that to get that encrypted data, and it will go around like 10 rounds. So we are using like AES 128. This is a standard here. So finally, we will get the encrypted output, and the same applies for de-encrypted output. So it will go on the inverse operations like inverse subbytes, inverse shift rows, mixed columns, and everything. So it is this idea is totally about cryptography, and we had implemented this in Vivado and Jupyter Notebook. So I'll explain this algorithm in a while. So now we go into the Vivado. So this is a block diagram. So I first put that basic blocks like DMA and Smart Connect and processing system, and this is on custom IP. So I implemented this AES using high-level synthesis using Vitis, and wrote that AES logic in this C++ program and synthesized it to hardware IP, and I defined that interfaces. This generated a reusable IP block for Vivado. And coming to that Vivado, I imported that IP block so we can able to use it for our needs. So the flow is that first the processing system sends that input to this AES via DMA, and again this after performing all that logic, it again the data comes into processing system with the help of DMA. So the DMA act as a bridge here. So from this I connected all these clocks and reset and ensure that there's no mistake here, and we validate the design and there's no mistakes happening, and we generated a bit stream and everything. So and after that implementation, we will get a lookup table, and it shows that how the FPGA board is programmed, and after that we will generate a bit stream, and we can able to use it in our software. Thank you. So this is the software algorithm. So we are uploading that bit file and SWS file, and that Python file here. We are creating a Python file here to run that software simulations. So coming to the code, we are overlaying that bit stream, so the FPGA board is programmable. So right here I have added some debugging codes in between, so we can able to get what is the error we are getting right now, and right now it's like perfect. So I had implemented a UT F8 text encryption. So it's basically it will convert anything into encrypted data like emojis and different language and different text numbers. Okay. So right here, like I'm Tamil, so like we are encrypting the Tamil data here. So and also that we are implemented image encryption data. So I will show you the results. So it's like showing that bit stream is loaded properly, and we are able to get that detect that IPs and everything. So this is the text hello FPGA Tamil. So it is encrypted into 164.224. So we can't able to it is divided into bytes and everything. And after that we are getting that encrypted text, and from this we can able to figure we can't able to figure out what is the text actually means, and again it will go into the set of mathematical operations to get that what is that uh, encrypted data, and right here we are getting that data. And now this is image encryption text. So I had uploaded a demo image, and we can we're doing some image encryption, so people can't able to figure out what we are sharing. So and we can able to get that distorted image and lot of noise and everything. So this is also comes under math, and we also use again applying that inverse operation to get that de-encrypted data. So right here, this process is very fast. I think it got implemented in milliseconds. So the system successfully encrypts our input data, decrypts it back to original. This shows the correct AES functionality implemented on an FPGA board. And hardware execution is faster compared to software only. FPGA plays a key role here because it enables parallel processing, reduces computation time, and provides hardware level acceleration. Compared to CPU, FPGA perform multiple operations simultaneously, ideal for cryptographic application. This makes FPGA suitable for secure communication, real-time encryption, and embedded systems. So, yeah, this project demonstrates how hardware acceleration improves cryptographic performance. Thank you.